Okay, let's get to part 2 of this lesson, and we're going to rationalize the denominator, which, as I was just explaining at the end of the last video, is eliminating the radical from the denominator. So all you're doing is changing how the expression looks. You're not changing its value. It's like you changing clothes. You're still the same you on the inside, you just look different on the outside. So if we have the square root of 2 over 15, the problem there is that we have a radical in the denominator, and I can rewrite this as square root 2 over square root 15. So the way to change how this looks and to not have a radical in the denominator is going to be to multiply by a special form of 1. See, if I don't want to change the value of the expression, the only number I can multiply by is 1, and the only number I could add is 0 to not change the value. So I'm going to multiply by 1. I'm going to multiply by a special form of 1. So here's my 1. The special form of 1 I'm going to choose is square root 15 over square root 15. Because when we multiply those denominators, what do we get? Square root 15 times square root 15 is 15. And then how about the numerator? Square root 2 times square root 15 is square root 30. So our simplified expression, which doesn't necessarily look simpler than the original, it just doesn't have a radical in the denominator, is square root 30 over 15. And you can always check the original expression in your calculator, see what the decimal is, check the answer in your calculator, see what the decimal is, and make sure they're the same. Especially if you're uncertain if you did it right, or if there were lots of steps to do and you think you might have made a mistake somewhere. Okay, let's do number 12, but we can actually make it a little bit simpler before we go through the rationalizing process. Because what we can do is we can first just think of this as square root 17 over square root 12, but then let's change the square root 12. Let's make it 2 square root 3. Okay, so we're just simplifying square root 12 to start with. Now for our special form of 1 that we're going to multiply by, it doesn't need to be square root 12. All it needs to be is square root 3. Square root 3 over square root 3. Would it work if I started out and multiplied the top and bottom by square root 12? Yes, it would, but it would just mean more simplifying later. So I prefer to simplify early on and then rationalize. Okay, so we multiply our numerators. 17 times 3, that's what, 51? So we have square root 51. And then the denominator, the square roots multiply to give us 3, and then we also have the 2. So 2 times 3 is 6. All right, now 13 and 14 are a little bit different because we don't just have a radical in the denominator, we have a difference or a sum of terms, and one of them is a radical. And in other cases, maybe both of them are radicals, but you have a sum or a difference. So there's something else we need to do here. And this might remind you of something that we have done with factoring. So I'm going to kind of remind you, remember difference of squares? The difference of squares factoring formula was if you have to factor a squared minus b squared, it factors into a minus b times a plus b. Doesn't matter what order we write those in. And those are conjugates, one with a plus, one with a minus, otherwise they look the same. And what happens when you multiply conjugates? Of course you get the first, a squared, and then the outside is plus ab, the inside is minus ab, so the outside and inside cancel, and then you get the last minus b squared. So outsides and insides cancel with conjugates. So we can apply that to this problem. Outsides and insides cancel with conjugates. So what if the special form of 1 that we chose to multiply this expression by is actually the conjugate of the denominator? So 5 plus square root 2. So we need that on the top as well to make this a 1. What's going to happen when we multiply those denominators? Well, when we multiply the first, we get 25. When we multiply the outsides, we get 5 square root 2, and when we multiply the insides, we get negative 5 square root 2, so those cancel. So we don't even need to write that. And then when we multiply the lasts, we get minus 2. So the denominator is actually just 23. I'm going to leave the numerator as it is for the moment. So now we have 4 times the quantity 5 plus square root 2 over 23. At this point, we can go ahead and distribute the 4. I left it out temporarily because maybe in another problem, the number on the bottom is, say, 22 or 20 or something, and maybe that number will reduce with the 4 or whatever happens to be on the top. So might as well leave it factored out until you know. Okay. So if you're going to go ahead and multiply it back through, you would have your answer 20 plus 4 square root 2 all over 23. Okay, so just like we saw conjugates with factoring, if you have a plus square root b and a minus square root b, they are radical conjugates. Conjugates is going to be a topic that we use a lot for a variety of reasons over the course of the next few years. So let's try number 14. So what is the conjugate of the denominator? What are we going to multiply the top and bottom by? 4 minus square root 11. Okay, so the numerator is right now 2 times the quantity 4 minus square root 11. And the denominator, when we multiply the first, we get 16. Insides and outsides are going to cancel. And then minus, and then we multiply the last, and we get 11. So 16 minus 11. So we have 2 times something over 5. Doesn't look like that's going to reduce. So I'm going to go ahead and distribute the 2. And there we have the simplified expression, not because it looks simpler, but because it doesn't have a radical on the bottom. Okay, so we're going to wrap up this lesson by applying the idea of radicals to quadratic equations. Remember, we've been doing a whole chapter on quadratics, quadratic expressions, equations, functions, and one of our main goals is to learn different ways to solve quadratic equations. So there's a method called solve by square rooting. That we're going to look at today. And it doesn't work for every single quadratic equation, but when it works, it's a nice, simple method. So take a look at this equation here, number 15. Let's isolate x squared. In most linear equations, our goal is to isolate x. In this case, it's not linear. We're going to isolate x squared. So we'll start by adding 15 to both sides. So 2x squared equals 80. And then we divide by 2. Keep in mind that it's not this. It's not the 2x being squared. Remember, it's just the x that's being squared and then multiplied by 2. So the next step in order of operations is to divide by 2 and isolate the x squared. Now we're ready to square root both sides. And what are we doing? We are finding the square roots. So there's going to be 2. Plus or minus is needed. So plus or minus the square root of 40. That takes us back to the very beginning of our lesson when I said, is it different if I say this in words? Find the square roots of the number versus just using the symbol. Remember, the symbol, the square root sign, only means the positive or principal root. So if you want to represent both roots, you need the plus or minus. Lastly, let's go ahead and simplify the radical. 40 is 4 times 10, and the square root of 4 is 2. So we have x equals plus or minus 2 square root 10. We're going to leave it exact. There's no need to get a decimal. This is the exact answer. You only need to worry about decimals if it's a problem that requires or asks for decimals, and lots of times those will be some of our word problems. Okay, so if we kind of break it down to a procedure, what we had to do was take our equation and get it down to the point where it was something squared equals something, and at that point, you square root. So let's take a look at 16. We have 1/5 times something squared equals something. So let's get rid of the 1/5 by multiplying both sides of the equation by 5. Now we have something squared equals something. So we are ready to square root both sides. When you square root the left, it undoes the squaring, so you have z plus 3. When you square root the right, you have plus or minus square root 35. And then to get z by itself, we subtract 3 from both sides. So z equals negative 3 plus or minus square root 35. Okay, last thing is we're going to look at an application. And you may have some experience with physics problems where objects are dropped or thrown. And because of the acceleration due to gravity, there's actually a quadratic relationship between the height of the object and time. So in this problem, we're just looking at dropped objects that have no initial velocity. When an object is dropped, its height, h, in feet above the ground after t seconds can be modeled by this function. Now, the number that's in here, negative 16, it has to do with the acceleration due to gravity, which would be negative 32 feet per second squared, and that number is half of it. H naught, that's how we say this here, the H with a little 0, is called H naught. It's the object's initial height in feet. That means the height at time 0. The graph representing the height of an object dropped from an initial height of 200 feet is shown at the right. And the model assumes that the force of air resistance on the object is negligible. And it only works on Earth because we're using Earth's acceleration due to gravity. If you had a different planet or a different place other than Earth, you would have a stronger or weaker gravity. You would have a different number there. Okay, so let's take a look at this last example. For a science competition, students must design a container that prevents an egg from breaking when dropped from a height of 50 feet. Okay, it's dropped. We're assuming that we're on Earth. We know the initial height. How long does the container take to hit the ground? When it says how long, our goal is to find the time. So let's use the model. H equals negative 16 t squared plus h naught. We know the initial height is 50 feet. So we'll substitute that in. Do we know the final height? We do, because we're finding the time for it to hit the ground, and the ground would be a height of 0. So let's substitute our numbers in. 0 for the final height. We're solving for time. 50 for the initial height. I'm going to add 16t squared to both sides. Divide both sides by 16 to isolate the squared term. Leave it as an improper fraction. It's so much easier to square root things as improper fractions than it would be as a decimal. Now we're going to square root. Square root both sides of the equation. We need plus or minus. Square root of 50 over square root of 16. You can break it up like that. And we know that 16 is a perfect square, so the denominator is just 4. And we know that 50 has 25 as a factor. If we factor the 5 out, we have 5 square root 2. So plus or minus 5 square root 2 over 4. But in the context of the situation, we're not going to have a negative time. So eliminate the negative time. That's extraneous in the context of the problem we're doing. And this is a good time to find an approximate answer, because we don't normally say, oh, it took me 5 square root 2 over 4 seconds to do this particular thing. We would normally put it in terms of just numbers. So if I put that in my calculator, we get approximately 1.8 seconds. So always find the exact number, because we're doing math class and we care about precision, but also when it's appropriate, you could find the approximate number. And again, we're eliminating that negative. Okay. So this is your assignment. There's a little bit I'd like you to try on the calculator, and it's basically the dropping of the object problem. They gave you a couple of them, and you can use your calculator to solve them and find the approximate answer that way. And then we have some problems from section 4.5. Thanks, everybody.